Good morning, everyone. Thank you for your kind invitation that we can get the opportunity to present iDAI.field today in this setting here. Yesterday, we already participated in the workshop, and for some of those who have been there, some of the things I'm going to say now may be a little bit redundant, but I think for the general audience, it's quite good to start with a little bit of an introduction. As you have said, iDAI.field is a software for documenting and publishing archaeological field work, which is developed by the German Archaeological Institute in its head office in Berlin, together since 2023, with the head office of the Common Library Network, for which is Thomas working, in a collaboration within the NFDI for objects, so the National Research Data Infrastructure Framework, which at the moment is a big project in Germany. So, before we start and have a look at the application itself, I want to give you some introductory remarks on the Institute and on its development history so that you can get a little bit the context in which we are developing and using field, because I think it's quite different from what you are doing on your daily basis. So the Institute has quite a long history. It was founded 1829 in Rome, and since 1874, we are part of the, or we are a federal agency under the Foreign Office of Germany. Currently, we have more or less, depending a little bit on how you're counting, 19 permanent branches and sub-branches, and more than 300 projects and excavations worldwide. Our excavations are generally limited to research excavations, and virtually all of our activities take place outside of Germany in cooperation with partner institutions in the host countries. Some of our major projects, such as Pergamon and Olympia, for example, have quite a long history, in some cases spanning more than a century of more or less continuous excavations with some obvious breaks in the past. Consequently, our information infrastructure must take into account a wide variety of domain-specific as well as local, mostly multilingual documentation requirements from our different projects. Using databases to document archaeological field research has a long tradition at the Institute. Not as long as this quote from Jean-Claude Gardin might suggest, but I think probably 30, more likely 40 years of history. In some cases, some pioneers already started earlier than that with the usage of databases to document their field work. Initially, there have been many individual databases, all of which were created and used by individual archaeologists with different technologies and data models in the context of one specific project. However, providing and maintaining and administrating such individual solutions was costly, and the resulting data was so heterogeneous that it was impossible to bring those different projects together. The end of life of the databases was usually reached at the end of the project, and a really long-term availability of the data could never be guaranteed. So this goal formulated by Gardin of making archaeological data openly available still remained then out of reach of the Institute. In an attempt to address those shortcomings, work began in 2006 to develop a unified relational database, then called iDAI.field. Now we say iDAI.field 1 to distinguish it from the newer versions. There a model was created based on our Pergamon excavation, which shows in the data model itself. And individual projects could then customize the database to their needs by adapting the data model and by adding project-specific extensions. This adaptation, however, was time-consuming and from a technical point of view, not easily done. An evaluation of the data stored also revealed a number of data quality issues, including the excessive use of free text fields and simultaneous input in multiple languages. So normally we document in English, German, and the language in the host country. And people tended to use free text fields to mix those languages together, which was very hard later on to use for data retrieval and find specific things for people who have not been involved in the project. In the end, the databases were operated again more as data silos without any really attempt to ensure comparability at the data level. In addition to that, there have been also fundamental problems with the proprietary software we have used, such as high costs for hosting it and problems with backwards comparability when they changed between versions, and we had to exchange our software to accommodate the new version of the database. But since the idea of a unified database was in theory still very well received at the Institute, and there was still a strong desire to generate and publish comparable data, it was then decided to take a new approach to address those shortcomings of the first version. So in 2016, the Institute started the development of a completely new software based on only open source technologies. For that, a set of fundamental requirements was established beforehand. And the technology has been chosen accordingly. This involved many trade-offs, and we really had to weigh up the individual requirements against each other. The most important key requirements are a flexible data model that could accommodate all our very diverse and heterogeneous field research, but with mechanisms to ensure good data quality and comparability. Really important for us was an offline-first capability with a robust synchronization mechanism, so that we could work in areas where we have no internet connection at all, or in the magazine, or somewhere where you cannot connect to a even a local network. Also, we wanted the possibility to really document in multiple languages and the technology that could support this. For us, it was important that the application should be able to run on all operation systems and that it was easy to use for students without any extensive training beforehand. And as I already said, open source technologies should only be used to avoid dependency on proprietary technologies. Also, our institute in its software development has a tradition of supporting open source and only trying to use open source technologies if it could not be avoided to do it otherwise. So to meet the requirements I laid out, various technologies have been evaluated. The choice ultimately fell on Electron as a platform, which is a framework that provides an excellent foundation for cross-platform desktop applications. PouchDB was chosen for the client-side database and CouchDB for the server-side. Both of those are document databases which store just JSON, plain JSON, or JSON documents. And here the decisive factor has been the offline-first functionality and the flexibility of the data model, which can be handled by the document data model quite well. For the front end, we chose Angular, which is a long-established and proven open-source web framework that allows for a lot of flexibility in the design of user interfaces and is highly adaptable. This mix of technologies enables us to meet our requirements in line with our priorities. But on the other hand, choosing a technology always involves also trade-offs. So for example, our user management is significantly more difficult to implement with our choice than with other technologies. So from this starting point, the application grew over time until now. And now, in addition to the desktop application, iDAI.field includes a server component for synchronization and backup, as well as a publishing component that allows projects to be published and versioned. But before we have a closer look at those core features of the application, I want to give you a little bit more information about the data model, because to satisfy our requirements regarding flexibility and comparability, we decided on a model that consists of 3 building blocks. We have a core configuration with some super categories and application logic, which all projects have to use. We have a library, which is optional and has predefined categories and subcategories, fields, and value lists, which can be reused by all projects, but projects can choose out of this library. They do not have to take what is in there. And then we do have a project-specific configuration elements, which can be created within certain limits by the projects themselves. To customize their data model, projects can easily do that by now, since the third version or iteration of iDAI.field, via a graphical configuration editor. Therefore, no technical knowledge is needed to do that. At the same time, the editor enforces some constraints on the data model so that we can at least guarantee a certain kind of comparability of our data. So, for example, there are some mechanisms built into this configuration editor or configuration itself. As I already said, there are categories and subcategories. Subcategories can be added by the user. They extend their parent categories while inheriting configuration elements. So, for example, you can define a subcategory pottery of a find, which has then some specific values, but pottery will always be a find, so that at least you know we are talking about a find which cannot be deducted from the data model. So we can agree probably that most excavations deal with finds, but then you can go into specifics what kind of finds you have and what kind of values you need to document them. The application offers also mechanisms to reuse configuration elements for categories and value lists. You can export your whole configuration and import it into another project at the moment. And you can store URIs and reference resources such as Wikidata or links to controlled vocabularies or thesauri or SCOS elements with specific semantics within the configuration, so you can make quite clear what you want to express. In the future, but that's far future ahead, we really would like to make that even more flexible so that projects can exchange certain configuration elements. And we really get a consistency by offering projects to reuse what's already there and not start from scratch with their configuration via, for example, a kind of online marketplace or something like that. In addition to that, there's also a graphical user interface tool for troubleshooting data issues in the application. Since I said we really emphasize the offline first aspect of the application, people could, in theory, work offline on the same resource, and there have to be mechanisms to decide what to do when a conflict arises. So if two people enter data into the same field offline, the application has to have a way to handle that. And that is also implemented with a graphical user interface in the application, so that such conflicts, which in practice are quite uncommon because people do not tend to work on the same exact resource at the same time offline. But if that happens, it can be resolved easily. And as I already mentioned before, also too, multilingualism is not just a convenience feature for us, but we also feature to really ensure data quality. Therefore, we have set up a web tool that allows the collaborative translation of the interface and the data model, and there are already quite a lot of languages available for the interface. And the application now can handle data entries in multiple languages without any problems at all, because it can distinguish in its core which language it is, and you can use labels for your value list. So you could more or less use any language you want to within the application. And with that, I am going to hand over to Thomas.
Yes. Now let's take a closer look at what the desktop application looks like. So one of the main ideas behind Field Desktop is that viewing data in context makes it easier to identify connections. Field Desktop brings together data from different sources and in different formats: textual data, geospatial data, and image data. And in this screenshot, you can see that everything displayed on the map on the right is also displayed in the list on the left. And you can access the data of a trench or find without quitting the map view, and thus you are always aware of its context. Everything you manage in Field Desktop, trenches, stratigraphic units, finds, and so on, is referred to as a resource. And when creating such resources, you can choose from various categories. Here in the screenshot, we can see some of these predefined categories that come with the application. Data is entered using clear input forms. Which fields are available in the input form and how these fields are grouped depends on the selected category. For entering data, there are various types of input fields and widgets available, for example, for selecting values from drop-down lists, adding measurements or date specifications, or entering text, as Fabian has already mentioned, in multiple languages. To create these input forms and to define which categories and forms are available for selection in your project, we have seen this some minutes ago. The application includes a built-in configuration editor, and you can use this tool to customize the project configuration, which is the selection of fields, categories, and forms for your project. And you can choose from a range of predefined categories that come with a so-called configuration library that we have seen in the image before. And this is included in the application, or you can create your own categories, fields, and value lists, and you can sort them here into new groups, change the order of fields, customize labels, and this way you can tailor the whole thing to the requirements and needs for your project. The configuration editor also allows you to add metadata to the various configuration elements. For example, you can reference sources, create semantic links using S-cos relations, and you can document the definitions on which your fields and value lists are based in description texts. And this information, as we can see here, can then be viewed when creating or editing resources. Now, let's take a look at some other documentation tools that come with Field Desktop. One of them is the matrix view that we can see in this screenshot. So stratigraphic relations allow you to establish spatial or temporal links between resources, and based on these relations, Field Desktop automatically generates a matrix that can then optionally be grouped by phase or by time period. And you can export this matrix in the formats SVG or the Graphis dot file format and use it in other applications. Field Desktop also offers extensive options for managing images. You can upload drawings, photos, or georeferenced plans, which can then be displayed as map layers. You can manually add metadata to images or have certain metadata extracted automatically from the image files, such as the creation date or the name of the person who created the image. And of course, you can also link images to other resources. Using the inventory feature, finds and samples can be assigned to storage places to record exactly where a find or sample is currently stored. And in addition, you can use QR codes to identify objects and their storage places, as we can see here. QR codes can be generated directly from within the application, and you can also let Field Desktop print the labels for you. Here's one in German. That's what it looks like. However, if printed labels with QR codes are already available, these existing QR codes can also be used with Field Desktop. Once you have assigned QR codes, you can then quickly access the corresponding finds, samples, shapes, or boxes in the application at any time by clicking this QR code search button that we see here at the top, and then you can scan the code using the camera. Another feature of Field Desktop is the possibility to create type catalogs, to build typologies, form catalogs, or any other kind of classification. And that can then be used to reference other resources. Per default, or it can be used, it can be referenced by other resources as well, of course. And per default, type catalogs can be used in the project in which they were created, but you can also export them to reuse them in other projects. A relatively new module, which was added in one of the latest versions, concerns the ability to manage workflows within the application. This allows you to document all the processes taking place within your project, such as sampling or restoration processes or image creation. And basically any work steps where you wish to record who carried them out, when they were carried out, and which find or trench or whatever is affected by this process. And you can document all of these things using this workflow module. I've just mentioned that I can export type catalogs. However, that's also true for everything else recorded in Field Desktop. CSV is our main format for exporting resource data. And in addition, we support GeoJSON and shapefile for exporting geodata. And using the export function, you can back up data or share it, for example, to import it into another Field project that uses the same configuration. You can reformat data or continue to use it in other applications outside of Field Desktop. And the counterpart to this is the import function. By importing files, large amounts of resources can be edited quickly, geodata can be edited to existing resources, and of course, new resources can be imported. The import function supports the same formats as the export function and also a JSON-L, which is JSON lines format, which means one JSON object per line. And this was originally used internally by us during the development, but it is also freely usable and documented in the manual, just like all the other formats. To ensure high data quality in projects documented with Field Desktop, the application features a comprehensive warning system that automatically detects data inconsistencies and displays corresponding warnings. Such inconsistencies may occur, for example, during syncing, as Fabian already mentioned, or as we see here, if you remove values from a value list and the removed values have already been entered into resources. You would then see a warning that tells you there is an invalid value here that's not contained in the corresponding value list configured for this field. And the warning tool then allows you to quickly correct such entries for many resources at once. If, for example, the same value is entered in 200 resources, you can use this tool to replace the value in all 200 resources at once with a new value that's actually a part of the value list. This warning system is particularly helpful because it allows the project configuration to be adjusted at any time. One of our fundamental principles here is that adjusting the project configuration never automatically changes any data. For example, if you delete the category pottery from the configuration, not all pottery resources are immediately deleted from the project. Instead, these resources are only hidden, and a warning appears that tells you about the problem. And you can then decide, do I really want to delete these resources, or would I perhaps prefer to add the category pottery back to the configuration? And in that case, all pottery data becomes visible again. And in total, there are currently 70 different types of warnings, helping to ensure that field projects remain as clean as possible and free from data chaos. And to round up this overview of the basic functions of Field Desktop, I'd like to mention the option to set up automatic backups. This happens automatically in the background. For every field project there is on the computer, a backup file containing the latest version of the database is created continuously. And you can also set it up in a way that it keeps older backup files. For example, if you want one backup file to be kept for each day, or one per month, or one every 2 hours, you can set it up accordingly. And if you then want to see what the status of the project looked like 2 months ago, you can simply restore the backup file and check what the data looked like at that time and decide if you want to continue working with the project in this version or import some data into the current version of the project.
Okay, Field Desktop, which you have heard about mostly until now, is the component that most users will interact with on a daily basis. But as Fabian has already mentioned, it's not the only one of the 3 pieces that make up our iDAI.field ecosystem. As you already saw, Field Desktop is used as an offline-first desktop application made for data recording in the field and during find processing. Collaboration is local first, works at any kind of local network, even with a phone hotspot without internet. But there is, of course, more to archaeological field work and to archaeological work than offline data recording. So we also have an online synchronization component. It's called Field Hub, and it allows users to share their database and work together over the internet worldwide, which makes post-processing of excavation data much more flexible and also allows institutions centralized backups and data management. The DAI is hosting its own Field Hub instance for its projects. Since the synchronization server is also an open source product, any institution can run their own Field Hub and manage their project databases online, same as we do. Field Hub is also used to detect any technical problems with databases that you have on the server, as you can see here with a few intentionally created problems on a test server. It gives admins a compact overview of the institution's database usage, contains some pre-flight checks for publishing databases, such as scanning for missing images or for missing image rights specifications. And last but not least, as I just said, databases can be published. So the DAI has also developed a platform that allows projects to transparently present their databases to other researchers online. In its current state, FieldWeb is mainly a presentation platform, but we are working on a significant update, which will make it yet again much easier to reuse and analyze published databases, it has a strong focus on inter-project search and public APIs. Some of the DAI's many research projects have already published their data in this way. We've had many papers and different publications about iDAI.field workflows and use cases from various colleagues at the DAI in the last years. Since the first release of iDAI.field in 2018, adoption among DAI projects is rising continuously, with the number of projects that decide to publish their databases also growing more quickly in the last years. Projects at the DAI use iDAI.field mostly with their own individual configurations. We do not have a general configuration to be used by the whole institute, since our projects work in many different branches of archaeology in many different countries with many different methodologies. So iDAI.field handles this excellently, but we will also see, which Thomas will show you in a bit, that it's great at supporting a unified documentation system as well. So we're now supporting a total of 109 projects on our FieldHub instance, some of which have been used actively since the early days in like 2018 or even before that as test projects. But adoption is still growing, as you can see from the graph. And we already had a couple of new projects this year that, well, of course, you're not going to see in this because it's only up to 2025. What we can't actually tell you is how many projects outside the DAI use iDAI.field. We know we are in contact with a couple of projects and excavations that have no relation to the DAI but are using it. But since anyone can download and use it, and since it's free and open source, we don't actually have any numbers on how many projects outside of the DAI are using it. Of course, having all these projects on a central server affords the DAI not only the added security of scheduled backups, but also some more interesting insights into the overall usage of the documentation software in all the various excavations and countries that we have. We can see that the usage peaks in different excavation seasons of the many projects that we have. And the number of modifications over the years also shows us that we have a really growing adoption of iDAI.field as a documentation software in the last decade. So last spring, we had a peak of over 300,000 edits in 1 month. FieldHub and Field Desktop, with its option to replicate and distribute databases offline, do handle this workload really very well and robustly. And of course, another interesting perspective is always to see, like, what are people actually working on? Like, what are they documenting? What are they recording? And it's not, well, maybe it's not very surprising that one of the largest groups of things that people document is pottery and photographs, maybe photographs of pottery, I guess. Yeah. And with that, we want to show you a very different use case by another institution with somewhat stricter guidelines, the Archaeological Museum in Hamburg.
Yes, thank you. The Archaeological Museum Hamburg has one of the largest archaeological collections in northern Germany, with more than 1.5 million objects from Hamburg itself and other nearby regions. But it is also responsible for archaeological heritage management in the area of the city Hamburg itself and in the district Harburg, which is located south of Hamburg in the German state Lower Saxony. And in this context, one of the main objectives is maintaining a list of all the known find spots in Hamburg and Harburg. And currently there are about 3,500 known find places in Hamburg and 5,000 in Harburg. The most important goal is to protect and preserve the archaeological monuments at these find spots. And these can be settlements, for example, or burial grounds, fortifications, or archaeological finds of different types. And when an archaeological site is at risk of being lost due to construction work or agricultural activities, an archaeological excavation will be carried out to ensure, to secure as much information and scientific knowledge as possible from this endangered site. And all of this needs to be supported by an appropriate software solution. Originally, a custom software called ArchaeoDocs was developed, but after development was stopped by the responsible company, a new solution needed to be found. And this time the focus was on moving away from building a custom standalone solution and instead creating a system primarily based on existing tried and tested software components. And this new solution, which is referred to as the new ArchaeoDocs, contains of two major components. The first one is Phyla, or previously called EasyDB. It's a web-based software for data and media management developed by the German company Programmfabrik. And the other one is Field Desktop, and the server application Field Hub. So Phyla is a web application that runs in the browser. Here we see a screenshot. It is used for managing find spots and measures and for storing all the files like text documents that are created during the handling of these measures. And measures can be, for example, mapping processes, site inspections, construction site monitoring, or approval processes. And of course, here comes our field software into play. Such a measure can also be an archaeological excavation. Field Desktop is the software used for documenting these excavations. A range of custom and adjusted categories and files has been built with the Field Desktop configuration editor to be used for these excavation projects at the Archaeological Museum Hamburg. And these configuration elements are also shipped with the application in the form of the configuration template ArchaeoDocs that you can select when creating a new project in Field Desktop. When you create a new project, you will notice it's a part of the drop-down list there. So we have Phyla for documenting find spots and measures, and we have Field Desktop for documenting the archaeological excavations themselves. So now, how are these two systems connected? There's another software component that realizes this connection, and this is called the ArchaeoDocs servicer. It is a custom-built web service written in Python that is called by Phyla via a REST interface. The servicer itself then calls the REST interfaces of Phyla and Field Hub to perform a range of tasks. And there are most importantly two different types of tasks: creating field databases and performing file imports. How does it work exactly? So the first job of the servicer component is to create field projects automatically to make sure that people don't need to do that themselves. So whenever a measure of the supertype archaeological examination is created in Phyla, a message is sent to the servicer, which then creates a corresponding new field database in Field Hub, the server component with the ArchaeoDocs default configuration. And everyone working on that excavation can then just download the project in Field Desktop and start working immediately. And the second big task of the ArchaeoDocs servicer is performing import processes. And you might ask why this is necessary, as there is already an import function in Field Desktop itself. And the reason for this additional way of importing files in this context is that data is often provided by external excavation companies, which cannot be forced to use a specific software. And therefore, we need a way to make sure these companies can ingest their data into the system without necessarily using Field Desktop themselves. Files can be imported via the web interface of Phyla. And as soon as new import files arrive, these files are then sent to the ArchaeoDocs servicer, which reads them and decides which data should be ingested back into Phyla and which data should go into the corresponding field database. And the file names have to adhere to a defined naming pattern. And based on the file name, the format, and the configuration file used by the servicer, it decides which importer to use and where to put the result. Some files like CSV, shapefiles, and images can be imported into the field database, while others like PDF files or point clouds are not passed further and are just stored in the Phyla database. This new ArchaeoDocs system based on Phyla and Field has been launched in mid-2023. And since then, 233 field databases were created. But as these databases are created automatically, not all of them are already actively used, which means that people either enter data in Field Desktop or an excavation company delivered data for this project that was ingested into the field database. And currently, 104 of the projects are already being actively used, and the databases are generally a bit smaller in size than the ones used at the German Archaeological Institute. The largest one contains 10,321 resources at this time.
So as you see, there's a lot of data recorded in iDAI.field. Many projects use it in Hamburg at the DAI. But yeah, so what now? I mean, we have all the data in iDAI.field, but just inputting data somewhere and then ignoring it forever, that's not the kind of workflow that we want, right? So Field Desktop is explicitly not designed for analysis or processing of data, but Field is not a silo. everything entered into field can be exported in a number of ways, as you saw from the graphs I showed you and from Thomas's workflow for the Archaeological Museum Hamburg. So you can work with it further. Field Desktop has a powerful REST API that can be used to programmatically access and update all data. So you can import and export CSV files, images, geodata in your script, or even write extensions for other software that will work with data from iDAI.field. This way, data transformations, additions, corrections, or even migrations from other databases can easily be automated. This API is already utilized by a plugin for QGIS that was developed by Oliver Zapiak at the VZG, so Thomas institution. With Field Connect, users can import all their geodata and attributes into QGIS, work with it, visualize maps, find some distributions of their finds or whatever, and also edit all geodata and attributes, and of course send the export back to Field Desktop then. There is also an R client, which allows importing data directly from Field's database into R. And it can help you build something like small visualization applications or flexible reports from your project data on the fly, which can be a great time saver for like real yearly excavation reports and publications. A new R client for the Field Desktop API is already in development. So additionally, Field Desktop also lets users create backups, as Thomas has also already said, which contain the full database in human-readable text. All project data can easily be compiled into a package that is suitable for long-term archival as well, as all the data that Field stores is image or text-based without any proprietary formats. A feature that will automate the creation of such long-term archival suitable exports is already on the roadmap for one of the next versions that we will be developing. But as I said, it's also trivial to compile such an archive manually from the exports that are already provided. We have already mentioned it a couple of times. iDAI.field is a free and open source software, and we're very committed to the open source principles and to open science principles. You can use iDAI.field, be it Field Desktop, Field Hub, Field Web, on your own computer, in your own infrastructure, and there's no need to ask us, obviously. There are also many ways in which you can actually contribute to the future of iDAI.field if you so wish. We always welcome users who wish to add translations of UI elements or value lists, and we've set up this online system that makes it easier to add and contribute translations. So just contact us if you wish to add or correct some translations, and we will get you in touch with the people currently working on the requested language, or add a new language even. And of course, you can, and actually please do so if you find any, let us know of any bugs that you find or any problems that you notice with the application. So you can simply open an issue on GitHub. You can even, if you want to work on a feature, we have not had that many outside collaborators until now, but we always welcome people who would like to contribute. So just start or get in touch with us if you have any questions before. So if you are interested in news about Field, scan this QR code and consider signing up for our user mailing list. This is the link to it. You can also find a link to the user mailing list sign up page on our GitHub. It's the way we get in touch with most of the users that don't belong to the DAI, since, well, the average archaeologist, as we have noticed, is not necessarily on GitHub. By now, Field is really a long-running development effort, as you've already heard in the beginning and see from the many things that we have presented. It's only the three of us presenting here, but there are many more people who've shaped the application over the course of, well, we can say the last decade now. Be it as advisors or developers, so it's not only three of us, there was a big team of many people that have developed something or contributed in some way over the course of time. So yeah, thank you, David, again, for inviting us, and thank you all for your interest. I will just share the QR code again in case anyone wants to sign up. Sure.